Our meeting, 5 people are joining meanwhile, so let me briefly introduce our today's speaker. Our today's speaker is Martin Lamming, who got his PhD in 1988 from Oxford University and get it in atomic physics, in particular based on measuring lamp shifts. Then moved to what is SAO?
Smithsonian Astrophysical.
Smithsonian. I would think it's like Harvard Smithsonian.
Yes.
Yeah, I was confused.
The Smithsonian side and the Harvard side.
Yeah, to Smithsonian in 1989 and worked there for 1 year, and then moved to NRL, National.
The Naval Research Laboratory.
Naval Research Laboratory to work with George Daszak in 1990, and then became federal employee in 1999. And now his main expertise in abundances, in first injection potential, and now today we will be having a talk by Martin about first injection potential effect.
Okay.
So please go ahead.
So I go to screen one.
Your screen, yeah. Screen one, yes.
Okay, everyone see that?
Yeah.
Oh, okay. I've got a. Let me move that out of the way. Okay, so thank you, Gregory, for the invitation. Thank you to everyone for tuning in. I've changed my title a little bit. Still going to be about the first ionization potential, but I'm really interested in the things it tells us about the element abundances in solar wind, especially the slow-speed solar wind and its sources. For those of you who have never been to NRL, what you see here is a picture of the Naval Research Laboratory. That's these 3 lights from the Virginia side of the Potomac River. This was painted about 25 years ago. Those of you who have been there will recognize this as a highly romanticized view of the place. It doesn't always look like this. And those are the usual contractual obligation slides. Okay, first ionization potential effect. First discovered, or at least suspected, in 1963 by Stuart Potash. The paper was published in April '63, so that makes the FIP effect just a little bit older than I am. It was the subject of much controversy over the years, especially when I came into solar physics in about 1990. Whether it was real or not was still being strongly debated. Now I think it is settled that the FIP effect really happens, and I'm going to describe how we understand it in terms of the most modern models. The FIP effect is an abundance anomaly where elements that are ionized in the solar chromosphere, that's things like iron, silicon, and magnesium, are enhanced in abundance by a factor of about 3 or 4 in the solar corona and in the solar wind, or certain regions of the solar wind. So this is a little bit strange to understand how something in the chromosphere controls what happens in the corona. I'm showing you here on the right-hand side some data from Don Reeves from this paper here, and he's showing here abundances measured in solar energetic particles. And you can see here, he's chosen his events carefully to get a representative abundance pattern of the complete SEP event. Okay, and what he's seeing here are elements like we've got potassium, sodium, all the low FIP elements here are enhanced by a factor of, here it's about 2.5 to 3, and here are the high FIP elements. which are essentially unchanged. The models the data points are from Don Reams. The models I am showing here are for a closed coronal loop. So the idea is that the seed particles for SEPs come from the solar corona. And the two models are for shear and torsional Alfvén waves. But you can see it picks up very well the abundance pattern, except for zinc. And zinc is the least well observed of the elements in Don Reams' data set, so I'm sure there's a problem with the observation, not the model. By contrast, one thing I want to point out about this is that elements like sulfur, phosphorus, carbon, which are the lowest FIP, high FIP elements, 10 eV is the dividing line, these are behaving like high FIPs here, they're not really enhanced. By contrast, in the co-rotating interaction regions where the accelerator particles are picked up directly from the solar wind, not from the corona, and also in the slow wind shown in gray, sulfur, phosphorus, and carbon are enhanced. There is a qualitative difference in the FIP between the slow-speed solar wind and the closed-loop solar corona. And that's going to be one of the things I'm going to try and explain in this talk. The modern model we have looks something like this. You have coronal structures, either open field or closed field, and Alfvén waves are propagating in these structures. And every time the Alfvén waves pass through the chromosphere, either reflecting from it or propagating through it, something called the ponderomotive force acts on chromospheric ions and not neutrals, and this gives the ion-neutral separation that provides the FIP effect. So there's a series of papers I have written which explain this and develop it and refine, and I'm going to try and give a summary of some of this and explain how we get these different FIP patterns out of this particular model. And now for completeness, I want to show you fast wind. This is a region of solar wind where FIP effect is greatly reduced. We know this comes from polar coronal holes, or the fastest wind comes from the polar coronal holes. And you see here, we also pick up the same, with suitable modifications to the model, we pick up the same abundance variation. Again, for magenta is showing you a shear Alfvén wave, and the green line is showing you a torsional Alfvén wave on whichever structure we think we're looking at. Okay, so that's a summary of roughly what this talk is going to cover and where we're going to go. The plan of the talk, I want to spend a fair bit of time talking about the FIP model and the ponderomotive force. If you're hearing the word ponderomotive for the first time, don't be alarmed. I'm going to explain to you what it is, how it comes about. It's a slightly weird thing, but it is a perfectly natural MHD phenomenon. You don't need any special special circumstances to see it. And then I'll talk about how it applies in closed solar field and in open solar field. Okay, I'm not hearing any response. I assume everything is going okay.
So that's normal because everyone is muted. So if anything's not clear, we will disturb you. But typically wait at the end. Yeah.
This is the first time I've done this. I want to be sure that everything is going okay. Thank you. Okay, so ponderomotive force. What is the ponderomotive force? As a teenager, I was very interested in history, and I read a lot about military history. And the Dutch Navy encountered a problem in the 17th century. Two ships on the open ocean, if they got too close together, would be pushed together. They understood it in terms of the wave modes between the two ships are restricted by the boundary conditions opposed by the hulls. The wave modes on the outside are not restricted. So you have higher wave pressure here and here than you do here. And that pushes the ships together. This is one aspect of the ponderomotive force. Wave pressure is one component of the force. In the internet era, I've tried looking for a good reference to this, and I haven't been able to find it. though I did find a reference in a lecture by John Barrow, who's a cosmologist, about the same problem of the French Navy in the 1820s. Of course, what John Barrow was really interested in is the force on two conducting plates in the quantum vacuum. And this is what I came across first, of course, during my PhD days. This is an interesting phenomenon in quantum electrodynamics, known as the Casimir force. So wave pressure is part of the ponderomotive force. How does this arrive mathematically? If you take the linearized MHD momentum equation, and if you take the first order terms to derive wave dispersion relations, the sort of thing you would do in a solar physics graduate course, you won't find the ponderomotive force. You have to take the second order terms in small quantities. So here I'm showing you the J cross B term, and it's this term here, delta J cross delta B, gives you part origin of the ponderomotive force. You do have to include all of the terms, the second order terms in the MHD momentum equation to get the correct expression. You can calculate the ponderomotive acceleration, and here is the most fundamental expression for it. In the case that you have wave frequency much lower than ion cyclotron frequency, so you're in the MHD limit. And the important part about this acceleration is that it is independent of the ion mass and independent of the ion charge in the plasma. It only acts on charged particles, but it's independent of these two quantities. This means that as an agent of ion neutral separation, it will give you quite a different pattern of fractionation than any thermal process, which will have a dependence on the ion mass and also presumably the ion charge. You think about collision cross sections, collision rates, things like this. And it's also one of the curious things about the Fiff effect that I showed you in the previous slide is that it is almost independent of mass. So this is already a positive thing if you're looking for an explanation. In the WKB approximation, that is, if you have no wave reflection or refraction as the waves propagate, and you put in delta B parallel going as rho to the quarter, you end up with something that looks like the negative gradient of magnetic pressure. So we're back to wave pressure. This is not the full story, as I'm going to show you in the next slide, but you're talking about things to do with wave pressure in deriving the ponderomotive force. There are some various other ways of deriving the ponderomotive force. I've got a couple of derivations I know of where you either write down the Lagrangian for particles and wave and energy, and follow the Lagrangian prescription for equations of motion, or derive single particle equations of motions in the electromagnetic fields of an R-plane wave, and you will still derive this expression for the ponderomotive force. Both these derivations need fairly explicit properties of the R-plane wave. And it's a little bit difficult to see what is contributing to what. There are two other derivations I know of where you use more advanced thermodynamics, so you have to calculate the change in the Helmholtz free energy as a wave passes through a plasma. But the only wave property that's required here in 3 and 4 is the refractive index, or the relative permittivity. So that tells you where the force is coming from. It's particles and waves interacting through the refractive index. If waves carry significant part of energy and momentum in the solar atmosphere, and that they reflect or refract off the plasma must experience a reaction force, and that's the ponderomotive force. So this is a slightly unusual way of moving plasma around. It's a perfectly natural way, comes straight out of the MHD equations. The only real question is whether waves of strong enough intensity exist to make this force significant. And this is probably what, and I would argue that we're starting to see waves of this amplitude, starting from sort of mid-1990s when we had SOHO and TRACE. So we are realizing, I think, that waves are more important in the solar atmosphere than we had previously thought, and this is going to be one of the consequences. Ion neutral fractionation by the ponderomotive force. Well, that's the sort of introduction of the ponderomotive force. If anybody wants to ask a question about that, now would be a good time. Otherwise, I will press on and talk about the results of the solar closed field. Okay, let's press on. Okay, how do we implement this? What I do, I have a model loop. So I don't take account of the curvature. It's just a loop that is straightened out with a chromosphere added at each end. Those of you who heard Sven Wedemeyer's talk about the chromosphere a couple of months ago, very beautiful talk, by the way, lots of interesting details. Well, you're going to be disappointed because what I use here is the static 1D chromospheric model from Avret and Lerser. I will argue that the extra details, I won't say I don't need them, but to establish that I have the correct explanation, I don't think the extra details in the sort of modern chromospheric modeling are strictly necessary. The key things here are to get the run of density and temperature with altitude in the chromosphere. The other important thing about Avret and Lerser is that they also give you the hydrogen ionization balance. And when you look at it closely, you find that hydrogen in their model is more ionized than the local density and temperature would tell you for local thermodynamic equilibrium. And this is probably the result of acoustic shocks in the chromosphere. As a shock goes by, it will elevate the ionization. However, the ionization is quasi-steady, and this is because the ionization recombination rates for hydrogen are much slower than the rate at which shocks go by. So you have a more or less steady ionization state, elevated above its equilibrium value, but not changing dramatically. The same is true for the other high FIP elements. It is arguably not true for the low FIPs. They may respond to shocks, but as I showed you a few slides ago, the ponderomotive force doesn't care about the charge on an ion. So if you go from iron plus to iron double plus, it doesn't make any difference. The force is the same. So to a certain extent, we can ignore some of the chromospheric dynamics in modeling the FIP effect. So we have this straightened out loop, a chromosphere at each end, and then I have a force-free magnetic field in the chromosphere, which I've taken from the parameterization in an old paper by Grant Athay. An important point to note is that as a field emerges from the magnetic field emerges from the convection zone in a tightly bound fibril, as you enter the magnetic pressure dominated part of the atmosphere, the field expands out and it goes through a layer where the plasma beta equals 1. This is roughly where sound speed and Alfvén speed are equal. One assumption I make is all fractionation begins once you're above the beta equal 1 layer. Nothing happens below that. And I can talk more about why that is a little bit later on when you've heard more of the talk and the model. So one thing that I do have to add to the chromospheric model is the effect of waves, acoustic waves. I'm showing you roughly what happens. The top panel is a figure taken from Carlson et al. 2015, which is interpreting IRIS observations of the magnesium-2 line at about 2,800 angstroms. Here the blue line are the data, the gray lines are various models, and the red line is the best fit model. And here you see the amplitude of slow mode waves or acoustic waves in the chromosphere going up to around 7 kilometers per second at a column mass of 10 to the minus 1. And that corresponds to about, about 700 kilometers altitude in the chromosphere. My prescription for acoustic waves in the chromosphere follows this all very closely. It's based on a different physical argument, but I get this very, very closely. The bottom panels show snapshots from simulations. So this snapshot is from the Carlson et al. 2016, a sort of publicly available simulation from Bifrost, I believe. And here they've got roughly similar wave amplitude in red, but it increases higher up in the chromosphere. But this is varying all the time. It's not the way the waves behave is varying a lot. And so I take the average behavior from the observation here. And this panel here shows a simulation from Hegland et al., same group. And you see at a location, I think they've taken about 1,000 kilometers altitude in the chromosphere, and you see the variation of the velocity amplitude with time. And it's of order, 5 to 10 kilometers per second, plus or minus. So we're talking about, sound waves comparable of amplitude comparable to the local sound speed, which is what I have in the FIP models. The ponderomotive acceleration, here's our expression for it from a few slides ago. The fractionation is given by an expression like this. It's quite important, I think. This is almost the last equation in the talk, but there's quite a lot going on here, so we need to explain to you in some detail. So this is an exponential of a line integral through the fractionation region. A is the ponderomotive acceleration. Vs squared is the amplitude squared of the various longitudinal velocities. So we have the ion thermal speed, we've got microturbulence from the chromospheric model, we've got slow mode waves generated by the Alfvén wave driver, and a flow velocity. These mu n and mu I are collision frequencies. So of the element we're considering, this is the collision frequency of the neutral component, of the element when neutral, and this is the collision frequency of the element when ionized. And psi is the ionization fraction of the element we're considering. So suppose we're considering something like a low FIP element like iron. Psi is going to be very close to 1, so that this term drops out, and all you have is the exponential of A over Vs squared dz. If you have an element that's not so highly ionized, say carbon, this might be 99% ionized, but the departure of this bracket from 1 means you get a significant contribution from mu I, and that reduces the fractionation dramatically in conditions. So when the background gas is protons, you have to be almost completely ionized to fractionate, which will be different, as you'll see, when we have the background gas as hydrogen. So with this expression for the fractionation, what I do is compute Alfvén wave propagation on the magnetic structure we're interested in, and then evaluate the ponderomotive force in the chromosphere, and then compute the fractionation. Let me show you how all that works out. Excuse me. Here is the Alfvén wave amplitudes in the corona. I've chosen a resonant frequency, which is about half a wavelength long. So the chromosphere is here, and this is the whole coronal length of the loop. So you have half a wavelength trapped resonant wave in the loop. This is the wave fluxes in ergs per square centimeter per second. We're talking about wave fluxes in the 10 to the 6 range. So these are automatically wave fluxes that carry enough energy to heat the corona. The difference in wave flux is this dotted line here. And here is the ponderomotive force. Throughout the corona, it's very small. It's much less than solar gravity. But in the chromosphere, it goes very large. Well, the chromospheric portion of the solution is shown here. Here are the density and temperature profiles, as we've seen before. The important thing to notice is that the density has a strong density gradient at about 2150 kilometers altitude. And because the ponderomotive force is a derivative of electric field over magnetic field, this is where the ponderomotive force will be strong. Here I'm showing the ionization balance of various low FIP ions. So we've got iron, calcium, magnesium, silicon, and then here we have sulfur and carbon. These are not formally low FIPs, but they still have very high ionization, very high charge fractions. Here are the high FIP elements, and you could, on the low FIPs, we're going from 99% to 100% here. On the high FIPs, we're going from 0 to 100%, and you can see a variety of elements in here. I've only plotted chlorine because that was in one of the elements in Don Reedon's plot at the beginning. And you can see here, hydrogen is this thick line, and all the others are basically following the hydrogen. Here we are seeing the wave energy fluxes in the chromosphere. So this is a resonant wave, so we have a small amount of waves leaking out of the corona, and a few are reflected back up again. Here is the ponderomotive acceleration as a solid line, and you see a strong spike going above 10 to the 6 centimeters per second squared at this density gradient. The dotted line is the amplitude of slow mode waves generated by the Alfvén wave driver, and at the top of the chromosphere it's around 20 or 30 kilometers per second. And here are the fractionations relative to oxygen. So we've got iron, magnesium, silicon, sulfur, carbon, argon, neon, and helium. Notice the fractionation is all concentrated at the top of the chromosphere where the density gradient is strong. The helium and neon are depleted, which is interesting in itself. Sulfur, although it is 99.4% ionized, is not strongly fractionated because of this, the high cross-section that the high collision cross-section that the iron sees compared to the neutral. There's one way of thinking about it is that neutrals can diffuse back through the concentration gradient very easily. They're not picked up by the ponderomotive force, and this is what limits the fractionation here. So this is called a closed loop fractionation concentrated at the top of the chromosphere. So this is the model. I had variants on this calculation going for quite a long time. I was very pleased when I saw a paper from Dev Baker. Actually, I had this to review for the APJ, where they have a map of an active region. And you see fit bias here, concentrated at loop foot points, and they trace out where they think the loops are. And this is MDI magnetogram to corroborate this. The thing that really interested me was the non-thermal velocity, what they're showing here. This is non-thermal velocity along the line of sight. So we presume they're looking at the slow mode waves, not the Alfvén waves, at the foot points of the loops. And at the amplitudes they are finding, 20 to 30 kilometers per second, which was exactly what I thought they ought to be. So I was very pleased to see this. And this I think is an important observation for verifying that at least I'm not going wildly wrong. The other important thing is that the amplitudes of these slow mode waves are more consistent with plain or shear Alfvén waves than with torsional Alfvén waves, for reasons I don't want to get into now, but this has implications for how the waves are generated and what sort of coronal heating mechanisms we should be looking for. I mentioned that helium in my model is depleted. Helium is long known to be depleted in the solar wind. If the helium in the solar wind were depleted because of inefficient Coulomb drag or gravitational settling, the corona should have a lot of helium in it. In fact, it doesn't. We measured the helium with SUMA on SOHO in 2001, 2003. Here are the data. The helium line is this one, shown at 2 heights above the limb. The problem you have is scattered light, so the excess here compared to here, so this is the helium line, the others are all nitrogen too. The excess signal of the helium here compared to here is the coronal signal we're interested in, and when you go through all of the atomic physics and calculate the rates, you get a helium abundance of about 5%. We have experiments in the Naval Research Laboratory to try and improve on this. The Herschel rocket has flown. We have some calibration uncertainties, but the helium abundance is coming out about the same. Moreover, the helium abundance in the corona mimics that in the solar wind. It's low in the ecliptic and higher at the plus or minus latitudes. The reason I'm talking about the helium abundance is that this helium abundance only happens, this helium abundance depletion only happens if the waves are resonant with the coronal loop. And that, I think, only happens if the waves have a coronal origin. There is no way to guarantee that waves entering the loop from underneath will necessarily be resonant. So here I'm showing calculations of the helium abundance depletion relative to oxygen for a variety of loop lengths and magnetic fields. This was done by then, well, she wasn't a postdoc at this stage, she was a federal employee, Kara Rakowski. And you see here, as the wave hits the resonant frequency of the loop, the helium abundance depletes. Basically what is happening, all of the fractionation is being concentrated at the top of the chromosphere. This is where helium remains neutral, but everything else is ionized. So everything is accelerated into the corona, leaving the helium behind. We find strongest depletion for longest loops and the lowest magnetic field. So that is the longest wavelengths, which waves which reflect the most easiest. Here is another view of the same thing. This last one, we normalized the waves to give a consistent solar flip effect with frequency, and so iron over oxygen is kept the same with frequency. We're looking at the variation of helium over oxygen. This calculation keeps the total wave energy in the chromosphere loop chromosphere system the same, and varies the resonant property. And you see, you could even have the flip effect coming and going with different resonant properties. So a key thing from this explanation of the flip effect is that alpha plane waves that cause the flip effect must be generated in the corona, because that's the only way to guarantee resonance with the loop. How can this happen? Well, here is a simulation by one of my colleagues, Russ Dahlberg, and this is supposed to be a movie. There we go. This is a loop, straightened out chromosphere at each end, where foot points are shuffled, and you're seeing contours of temperature in the loop as magnetic field is stressed and energy released in nanoflares, causing localized heating events. Let's run it again. You can see the loop responding here. Here's a heating event. Energy is conducted down to the chromosphere at each end, and this is sort of the paradigm of how loops should be heated and filled, by heating in the corona followed by chromospheric evaporation. I asked Russ whether he could look at his simulation results and tell me what waves that the nanoflares were producing. He rolled his eyes and said, "You know how complicated these things are, there's no hope." And then he came back to me the next day and said, "But you know, Martin, I could tell you what the ponderomotive force is in the chromosphere. That's just electromagnetic fields to evaluate. I don't have to actually identify the waves." So I said, "Well, let's do that." And so he did that, and here it is. What you're seeing here in blue is the ponderomotive acceleration. Russ is a real physicist, so he works in MKS units. So this is, at the top is 6 by 10 to the 4 meters per second squared. So this would be 6 by 10 to the 6 centimeters per second squared. Recall, we need something above 10 to the 6 to get my coronal loop model to work, and it's correlated with the electron temperature, so the maximum temperature in the coronal portion of the loop. And you can see the ponderomotive acceleration is correlated with the temperature. Every time the temperature rises in the corona, the ponderomotive acceleration in the chromosphere spikes as well. And in the simulation Russ has done, the alpha plane speed in the loop is slightly larger than the electron thermal speed. So a heating event, you might expect waves to get down to the chromosphere before the heat conduction. So you would then be fractionating plasma before it is evaporated up again. So was actually a very nice support for my idea that waves cause the fractionation, and the waves are generated in the corona. Okay, that completes what I want to say about the closed field. I want to now talk about open field in the solar wind. Okay, this is a diagram I showed at the beginning but didn't talk about very much. Here is the open field, closed field. The important thing to notice is that when I show fractionation in this cartoon, I have one arrow going to the closed field region, because fractionation only happens at the top of the chromosphere. In the open field, it's going to transpire. Fractionation can occur at a much greater range of altitudes. So I've drawn 2 arrows just to emphasize that point. Let's see what happens. In the coronal hole model, I take a wave spectrum from Steve Cranmer's paper here, and I just have different waves of different frequencies at the important features in the wave energy spectrum. And I start the integration, I start the waves at around 500,000 kilometers above the solar photosphere, which is roughly where the waves are purely outgoing, and then integrate back. Here are what Cram would tell you are the wave amplitudes of height. So here is VPerp. So it's starting off with a few, so about 100 to 200 kilometers per second amplitude. Here is what the coronal hole wave amplitudes look like. Here are the wave amplitudes again in kilometers per second. Here is the wave action, the wave energy fluxes, outgoing and ingoing, and their differences. Again, I have no sources or sinks of wave energy in these calculations, so the differences are always flat. And here's the ponderomotive acceleration again, very, very small, except when you get to the the chromosphere, which will be at this end. Here is the chromospheric portions of the solution. The first row shows a fast wind model from a coronal hole which has a magnetic field once you enter the coronal hole of around 10 Gauss. So here are the wave fluxes in the chromosphere. I'm not showing you the ionization balance and chromospheric structure again because that was the same as before. Here are the wave fluxes in the chromosphere, and you can see at the density gradient, waves are strongly. So the assumption here is that waves are coming up from the photosphere and propagating outwards. And as they hit the density spike, much of the wave energy is reflected back down again. So the wave energy, the wave energy flux in the chromosphere looks qualitatively different to how it did in the closed loop. Here is the ponderomotive acceleration. Again, the same spike in the same place, 2150 kilometers, and now it's several times smaller than it was before. This spike is lower than 10 to the 6 centimeters per second squared. And here is the amplitude of the slow mode waves that the Alfvén waves generate. It's smaller here, but deeper in the chromosphere, it is a larger wave amplitude that the Alfvén waves generate. Here are the fractionations, and as you see, it's reduced. It's still roughly consistent with what is seen, for example, by Ulysses. Excuse me. Iron, magnesium, silicon, sulfur, carbon. And one important thing to notice here, I've taken the previous closed loop had a magnetic field of 30 Gauss. Here it's a coronal hole, I've taken 10 Gauss. Note that fractionation doesn't begin in this model until about 1400 kilometers above the photosphere. Nothing is happening here, although there is ponderomotive force in this region. One feature of the calculations that I haven't told you about, but I think is the correct way to implement, when the sound waves generated by the Alfvén wave driver have an amplitude larger than the local Alfvén speed, these sound waves will generate positive and negative going Alfvén waves by fire hose instability. And these counter-propagating Alfvén waves will cascade to small scales and cause so much mixing and turbulence that I argue that nothing can happen, no fractionation can happen in this degree of turbulence. By contrast, for a coronal hole model with a magnetic field of 30 Gauss, now this is very similar. I've just taken the largest amplitude wave here. I haven't put the whole spectrum of waves. You have qualitatively the same things happening, but fractionation now begins at the beta equal 1 layer because the Alfvén speed is higher. The sound waves generated by the Alfvén wave driver do not generate the same turbulence, and stronger fractionation occurs. The important thing to notice here is that the fractionation is now occurring much lower in the chromosphere, where hydrogen is basically neutral. And in this case, sulfur and carbon can be appreciably fractionated, like the other low FIPs. Helium and neon don't really change. So this is a qualitative difference in the FIP fractionation that I showed you in Don Reams's papers, Don Reams's plots at the beginning of the talk. I think this is an important development, an important observation, that we can possibly tell from the slow wind element abundance properties whether it originates in closed field or open field, which is a big step forward in trying to understand origin of the slow speed solar wind.
You have 5 more minutes.
Okay, yes, I have 1 or 2 more view graphs. So this is quite exciting to me. I want to say that Don Reams is not quite the first person to see this. Here is a paper from Joan Schmeltz and co-authors from 2012, which Kara and I spent a lot of time looking at. They have collected a number of FIP fractionation observations. In black, you see all the remote sensing, all the spectroscopic observations. So that's the black here. And you can see sulfur, phosphorus, carbon are behaving like high FIPs. And again here, this is Phillips et al. The sulfur, phosphorus, carbon are very high FIPs. In blue, they've confused SEPs and co-rotating interaction regions, but you can see here that the SEPs, sulfur, phosphorus, carbon, are lower than the co-rotating interaction region, sulfur, phosphorus, carbon, and also higher yet again are the solar wind observations of von Steiger et al. So the anomaly I mentioned at the beginning is also visible in this plot, although these authors didn't comment on it. Kara and I noticed it, and we've been thinking about this ever since. So the key thing I want to emphasize is that in the variation of the sulfur abundance in the solar wind, if you have a low sulfur to oxygen fractionation, then fractionation must be happening in a background gas that is significantly ionized. The hydrogen is significantly ionized, sulfur behaves high FIP, and this means that you have fractionation at the top of the chromosphere, and it's probably coming from a closed coronal loop. If you have high sulfur to oxygen fractionation, you must be fractionating in background neutral hydrogen, and that means you have to be fractionating lower in the chromosphere, and this presumably happens in an open field. And this is an important clue to the solar wind. Some of you may know that the modern idea of the slow-speed solar wind origin is that it forms by interchange reconnection. Material that is in closed loops and material in open loops can meet, and reconnection between the two structures can allow closed loop material to escape into the solar wind. The exact contribution of this of plasma from each process and precisely how the interchange reconnection occurs is still subject to significant debate. And I'm hoping that from the microphysics point of view, that is element abundances and waves, we can make significant contribution to this type of science. So just a summary, of course this is all going to be important, the solar orbiter and possibly solar probe plus. The big picture, the connection with outplane waves in terms of FIP fractionation offers novel and unexpected diagnostics of wave motions in the chromosphere and corona. We can start to understand how the waves are generated, possibly how they're damped, the processes that heat the corona, and we should see wave correlations with abundances. So it's the second point. Abundances in the solar wind should correlate with the solar wave, with the waves and turbulence and trains in the solar wind. There is something of that seen already, and there's quite a bit of work going on to sort of emphasize this. Are slow wind and closed loop corona fractionations exactly the same? I would argue they're not. This has been assuming that the slow wind and closed loop corona were the same was the impetus for the interchange reconnection idea, but I'm arguing that they're actually subtly different, and the interchange reconnection needs to be not as obvious. There are some subtle details that need to be figured out there. And then, in general, big picture thing, the further connections of the wave physics with local helioseismology offers another open way to understand wave physics in the outer solar atmosphere. Okay, that's what I have. Thank you for your attention. I'll be happy to take any questions.
Thank you for interesting talk and excellent timing, Martin. So we are open to questions and discussions. I'm just looking for microphone. If someone has a question, you can unmute your microphone and just go ahead and ask. So far, I see that microphone is still muted. I have.
I've blown their mind.
Yeah, I have a question, but still everyone is invited to unmute and ask. So basically, one question I have is how fast this fractionation develops in the model, and how this timing is consistent with what is observed. It needs time to develop fractionation. Yeah?
Fractionation, certainly in the closed-loop model, is happening over a very small length region, a sort of few tens of kilometers. So I would argue the fractionation in the chromosphere is going to happen very quickly once the waves are there. Order of minutes, probably. To communicate that fractionation to the rest of the coronal loop, which has to happen by some quasi-thermal transport processes, chromospheric evaporation, diffusion, things like that. That's a scale of order, hours to days. And there are observations of loop abundances varying on the order of several hours to days. But that's based on sort of quasi-thermal transport. It's not especially interesting physics. The fractionation by the ponderomotive force, we haven't really been able to observe how quickly that happens. I haven't actually done detailed modeling of the time dependence of the fractionation yet, but just taking the length scale over which the fractionation happens divided by a simple flow speed, you see how it has to be. I should say that
yeah,
fractionation.
I think it would be really interesting to see which parameter drive the speed or timing of this effect. In particular, compared with observation, but as you said, it takes hours, days. Yeah.
Yes. In the coronal loop, that has been observed and it's been done. In the chromosphere, it's a very difficult place to make such detailed spectroscopic observations because there are so many dynamics, and to understand that you are seeing real FIP effect fractionation as opposed to something else would be quite a difficult thing to do, I think. Maybe Iris with Bifrost will get there, but it's quite a challenging observation.
Yeah, I agree. And I have one more question. In particular, I wonder in twisted flux tubes, and I know that properties of Alfvén waves excited on top of twisted magnetic field, where curl B is non-zero, are different from just conventional Alfvén waves. And in particular, such waves contain a non-zero DC electric field, which increases with intensity of ensemble of Alfvén waves. I wonder, have you considered inclusion of this effect and electric current effects in the model?
I haven't included consideration of electric current effects. I've considered waves on I should say everything I described to you was waves on an absolutely straight magnetic field. Twisted magnetic field it'll introduce currents. It'll also change the way the waves propagate. Yep. You no longer have a clean distinction between Alfvén waves and first mode waves. Everything I've done here was Alfvén waves, which essentially don't dissipate. If you have twisted magnetic field, the Alfvén waves and first mode waves are mixed, so you have to consider wave damping as well as propagation. That's going to change things subtly. The electric current effects, I haven't really thought too hard about, but in my sort of, unless the currents if the currents are important in fractionation, they must presumably be closing inside the sun. And I'd always assumed, maybe naively, but always assumed that you might get FIP effect at one foot point and inverse FIP at the other foot point in that case. The other important thing is that the force associated with electric currents is not going to be mass. The force is mass independent, the acceleration is mass dependent. So it's not clear to me that you get the correct fractionation pattern. I think the key thing with the ponderomotive force is that the acceleration doesn't depend on ion mass. and that means you have, I can calculate the fractionation for 20 or 30 ions, and you saw that in the Reams case, almost everything works. That's, I think, a big advantage of the ponderer motive force. Once you start thinking about it, there are many, many other things that could fractionate plasma, and there are various diffusions, various adiabatic invariants that can also fractionate abundances. And some of those I've thought about, some of them I haven't, but I would still argue that the ponderer motive force is the most important one.
Okay, thank you. So, last chance to ask a question or make a comment. Okay. The microphone muted, so let me thank everyone and thank our speaker again for this nice presentation.
Oh, thank you.
Yeah.
Thank you for the invitation.